In this lecture, we're going to be discussing stream processing. Now, stream processing is a very old branch of distributed computing, but in the last few years, it has come into the prominence because of the new workloads that we are seeing. And one of the systems that has become very popular is the STORM system, and we'll be discussing some of the details of STORM in this lecture. So we'll discuss why stream processing is important in today's workloads, and then also we'll discuss some design details of STORM. So today's workloads involve large amounts of data, whether these are feeds in a social network or whether they are information, click-through information from particular websites or from advertisement networks, or whether they are logs of accesses in any distributed computing infrastructure. So when you have such large amounts of information, you need some real-time view of these of this data so that they can be compressed and they can be distilled down into a form that is digestible to human users. So for instance, in social networks, you have the capability of search, and this is often real-time search, as you might find in the Twitter social network, where you can do a real-time search of the tweets that are being put out right now on a particular topic or with a particular keyword. When you have websites which are collecting data about who is visiting the websites, you may want to do website statistics, for instance, analytics via Google Analytics. Also, you might want to detect who are the intruders into your distributed cluster. For instance, most data centers are running some form of intrusion detection system or the other, and all of these require real-time analysis of the data that's coming in. Essentially, real-time analysis means that you have large amounts of data and you need to process very large amounts of data within a few seconds with very low latencies and with very high throughput, as much data per second as possible. And you want to produce some amount of knowledge or information out of that data that you're getting. So you want to convert data into knowledge, but fairly quickly. Even if the data cannot be processed completely, you want to still be able to glean some information out of it at least. So that's a stream processing challenge. And of course, you might think, well, the MapReduce system is available and we've already used it for batch computing before. Why not just use it? And in fact, there are variants of MapReduce that are aimed at stream processing. But essentially, MapReduce is a batch processing framework, and you need to wait for an entire computation on a large data set to complete before you can get the results. There is no notion of partial results in MapReduce at all. Even the variants of MapReduce that are tuned to stream processing or to incremental processing, there are incremental versions of MapReduce as well, still have a fairly high latency. And essentially, MapReduce is not intended for stream processing applications, and essentially it's not intended to be a long-running application, which is what stream processing really is. So the STORM system has become very popular in the last few years. It's an Apache project in the Apache Incubator. It's one of the more highly active JVM projects today. Multiple languages are supported in the API, including Python and Ruby. And STORM, as is today, is used by many companies, including Twitter, for personalization and for search. So every time you do a Twitter search, you're likely using indirectly the STORM system that Twitter is running in their data centers. Flipboard uses STORM for generating custom feeds, and a variety of other companies and websites use STORM as well, including the Weather Channel, WebMD.com, and others. So STORM consists of many components, and the 5 major keywords in STORM are tuples, streams, spouts, bolts, and topologies. We'll study these, what these are, over the next few slides. So a tuple is essentially an ordered list of elements. For instance, a tuple might be, in the Twitter world, a tweeter followed by the tweet itself. For instance, a tuple might be the tweeter name, which is Miley Cyrus, followed by the tweet which says, hey, here's my new song. A different tuple might be a different tweeter, Justin Bieber, followed by the tweet itself, hey, here's my new song. In a different world where you're collecting click-through logs, the tuple might be the URL followed by the IP of the clicker client, then the date and the time. For instance, the URL might be coursera.org. The IP is 101.201.301.401. Then you have the date and the time. A different tuple might be from a different client, 901.801.701.601, and then a slightly later time. Okay, so each of these is a tuple, and you want to process these tuples. You don't have just one tuple, as you have seen here. You have multiple tuples, and so a stream is said to be a sequence of tuples, potentially unbounded, which means that the stream might contain potentially infinite number of tuples. For instance, in our social network example, we could have all the tweets that are being put out there be a stream. So for instance, the Miley Cyrus tweet followed by the Justin Bieber tweet followed by a tweet by Rolling Stones that says, here's my old song that's still a super hit, and so on and so forth. You can have other tuples coming in as well. Similarly, in the website example, the two tuples we discussed might be part of a stream that contain other tuples as well. Essentially, you have a sequence of tuples coming in or a stream, and you need to process these tuples potentially one tuple at a time. Well, who generates these tuples? The process or entity that generates these tuples is known as the spout in Storm. A spout is the source of streams. Often the spout reads from a crawler or from a database. For instance, it might be reading from a database, in the case of Twitter, the database that contains the actual tweets that are being posted. Or in the case of a web analytics application, it might be reading from a crawler that is crawling the proxy logs of a particular web page. So a spout can generate multiple streams. So here I have a green stream of green tuples and an orange stream of orange tuples being generated simultaneously by the same spout. How do you process these streams? Well, the entity that processes a stream is known as a bolt in Storm. A bolt processes input streams, typically just one input stream, but it can process multiple input streams as well. And in turn, it generates an output stream, which is then fed to other bolts. In this example, I have a spout on the left generating a green stream for the first bolt, which processes one tuple at a time, maybe multiple tuples at a time, and generates some output tuples, in this case the purple tuples, which are then fed as input to another bolt over here, the second bolt, which then generates yellow tuples, which are then fed potentially to another bolt, and so on and so forth. So a bolt is essentially a program that is given as input one or more streams and then decides when it gets tuples from these multiple streams or from just one stream, whichever are its input streams, it decides how to generate output bolts. Okay, so that's typically the code you would be writing when you write a Storm application. You'll be writing code for each of the bolts in your application. And your application essentially consists of a series of bolts connected in a topology. So a directed graph of spouts and bolts along with output bolts is called a topology, and that's essentially equivalent or corresponds to a Storm application. So in this case, I have 3 bolts in my application, one spout, and one of these bolts is the output bolt. The rightmost bolt is the output bolt. And as shown here, essentially you would write code for each of these 3 bolts in the system as per your application requirements. And then the final bolt, the rightmost bolt, would generate some output bolts for you. Now, topologies are essentially directed graphs, and topologies may contain loops as well. They can have cycles, as is shown over here, if your application in fact requires it. But of course, when you're coding cycles, you have to be careful that you're not creating infinite loops, so that you need to be sure that tuples are not going around in the system forever. You need to make sure that tuples are in fact being processed, and then within some amount of time they leave the system. They don't stay around forever. So bolts themselves, the entity that processes streams, can come in many different flavors. 3 of the more popular flavors are filter, join, and apply. A filter essentially forwards a tuple only if it satisfies a condition. So that's essentially very similar to the SQL filtering notion. A join has a bolt receiving multiple streams. Say it receives 2 streams A and B. It computes a cross product of all the tuples in streams A and B. And for every pair of tuples, one from A, one from B, it then checks whether it satisfies a condition, and if it does, then it outputs something, okay? Perhaps something from those 2 tuples. That's again very similar to the notion of a database join. Finally, you have an apply or transform, which takes a tuple and modifies it according to a function, perhaps even according to a filter function. And there are, of course, many other functions that bolts can implement. In fact, you can write up your own bolt functionality that either uses these functionalities or doesn't, implements a new functionality. But no matter what bolt you implement, the bolt needs to process a lot of data. Remember that we are having very large amounts of data coming in. There are potentially gigabytes per second, maybe even terabytes per second coming into each bolt. And you need to process this large amount of data and process it fast. So in order to make each bolt fast, you can parallelize bolts. You can parallelize a bolt into multiple processes or tasks. So a bolt might consist of multiple tasks, and the incoming stream into that bolt is split among these tasks. Typically, each incoming tuple goes to one task in the bolt, but it might also go to multiple tasks. How an incoming tuple is routed among the tasks in a given bolt is decided by what is known as the grouping strategy. So there are 3 types of grouping that are popular, which decide how the tuples of a stream are distributed among the tasks of the bolt to which that stream is going to. So the first is shuffle grouping, which distributes the tuples of a stream evenly among the tasks of the bolt, and this is done in a round-robin fashion. So essentially, as you receive tuples, you go through the tasks in a sequential order, giving each task one or a batch of tuples, and then you loop back around to the beginning of that list of tasks, and then you do that again for the incoming tuples. However, this may not be what you want, because you may need to group the tuples based on some fields or a subset of its fields. This is where fields grouping comes into play. So here you group a stream by a subset of its fields. For instance, you may want to have all the tweets, all the tuples, where the Twitter username starts with A through M or 0 through 4 to go to task 1, and the remaining tuples to go to task 2. This allows you to, for instance, aggregate those individual classes of usernames, and this is done via fields grouping. Finally, you have all grouping as well, where all the tasks of the bolt receive all the input tuples. This is especially useful for joins. For instance, if you're trying to join the incoming stream with some other stream or with an existing database, then this is fairly useful for an all grouping. How is the Storm cluster itself run? Let's discuss a little bit about the infrastructure components. So the Storm cluster is run by a master node, again elected using leader election. The master node runs a daemon called Nimbus, and Nimbus is responsible for 3 functionalities, among others. It's responsible for distributing code around the cluster. So when a bolt is started up on another server, Nimbus is responsible for sending the code for that bolt to that particular server. It's responsible for assigning tasks to machines. So when a bolt is split up into multiple tasks, which task runs on which servers, that's decided by Nimbus. Also, Nimbus is responsible for failure detection. If any of these servers running bolts crashes, Nimbus needs to detect this and then potentially restart the tasks or the bolts on other servers. The servers themselves are running the worker node. This is run via a daemon known as a supervisor. This listens for work assigned to its machines, so it talks to the Nimbus server, and it also keeps track of the tasks that are running at itself, so that if any of these tasks crashes, it can then be either restarted, or the Nimbus daemon can be asked by the supervisor for a new task that needs to be run in its place. Storm also uses the Zookeeper system, which you've seen elsewhere in this course, which helps coordinate between the Nimbus and the supervisors and keep all the state of the supervisors and the Nimbus in a consistent place, so that if any of these crashes, you can then recover using what's kept in the Zookeeper system itself. What do you do with failures? So of course you can have failures. A server might crash while it is in the midst of processing a tuple, and if it does so, then those tuples might be lost. Any of the tuples that are in transit at that server might be lost. Okay, so in order to tackle this, Storm uses what is known as anchoring, where you can anchor an output to one or more of its input tuples. Okay, and the failure of this output tuple to be received causes one or more of those tuples to be replayed in the system. The way you do this is via an API, which is specified in the output collector class. This has 3 major functions: emit, ack, and fail. Emit essentially emits an output tuple, perhaps anchored to an input tuple, and if you want to anchor to an input tuple, you specify that as the first argument in emit. You can acknowledge that a tuple has been done by calling the ack function, and this means that the spout will now know that, hey, this input tuple that I had generated has been processed by the last bolt in the topology. Or you can fail a tuple. This immediately fails the spout tuple at the root of the tuple topology, and if so, then you would start replaying the tuples that have been missed as specified in the fail function itself. Okay, this might be done, for instance, if there is a failure or if there is an exception from the database, and so on and so forth. Typically, you need to be in Storm, at least in the current version, you need to remember to explicitly acknowledge or fail each tuple. There is no implicit failure detection of the tuples themselves. And if you don't do so, then you can certainly miss tuples that will not be processed because of failures, but also because tuples consume memory. You might have memory leaks because the tuples might stay around forever inside a particular server and never be garbage collected. So in order to prevent this, you need to make sure that you use ack or fail in a consistent manner, in an explicit manner across all the tuples that you're processing. So to wrap up our discussion of stream processing and Storm, processing data, large amounts of data in real-time systems, in today's systems in real time within a few seconds is a big requirement. And although stream processing systems have been around for a long period of time, for instance, IBM has had a very long running project called Streams, which is a very popular and widely used proprietary system. One of the newer open source systems that has emerged for processing streams today is Storm, or Apache Storm. There are many sister systems that have emerged as an offshoot of Storm, for instance, Spark Streaming from Berkeley. But in essence, Storm allows you to process large amounts of data, large streams in very short periods of time with very high throughput. To do this, it uses parallelism. It allows you to write up arbitrary applications using application topologies, and it also supports some notion of fault tolerance.